So this presentation is concerned with the amino acids, and just some general ideas about the amino acids, some physical properties. One of the things we want to also look at is, of course, the zwitterionic nature of these amino acids. So how does the pH perturb the species? And that can be done by thorough pK analysis. We'll also look at some synthetic procedures that occur with these amino acids. We should realize by now that we're not going to be too deep into it. We'll just briefly look at a number of syntheses that we've already looked at in the past, such as the alpha attack of the ammonia on the alpha brominated acid. We'll also look at the malonic ester synthesis of these acids, and then of course something kind of new, but it's not that novel, the Strecker synthesis for amino acids. And then we'll just look at the peptides themselves. What exactly are these peptides? So if we push on, why do we do this? Well, you can see that these amino acids are involved in everything. You see, it's like DNA, you can bring in RNA, and see some proteins here. You have some metabolites. Yeah, the proteins themselves are polymers. Yeah, that consist of bits of peptides, and really, yeah, these species are polymers of amino acids. So amino acids, yeah, are the monomers that are involved in peptides, yeah, and bigger, massive proteins. You can see here, for example, the structure of the amino acid is typically just simply an acid group, and the acid group on the alpha carbon, yeah, has an amino group. On the alpha carbon has an R group. So apart from glycine, which has both species on this alpha carbon are hydrogens, so it's non-chiral. Every other amino acid will have a chiral center here at the alpha carbon. There's 20 naturally occurring amino acids. 10 of them are essential. We have to go out and consume them. On the other hand, 10 we can synthesize ourselves. There is a D and L designation for these guys. We can look at that later. So here we have glycine. As I said to you before, it's achiral. But then you can see that we have here, for example, yeah, the general amino acid. It's predominantly L, yeah, meaning that if you look at the fissure, the R group is on the left. The enantiomer, of course, is D's, and of course these are not common at all in nature. When you look at the chiral center, in most cases these are R, yeah, but of course cysteine has a S configuration. We use one letter or three letters, more commonly three-letter abbreviations, to denote our acids. You can see here we have the 20 amino acids that we use, and you can see here, for example, in isoleucine, we have a isobutyl group on the amino acidic species. Yeah, so that is the R group, yeah, that is present on isoleucine. You should realize that it is a hydrocarbon, so this then therefore is a neutral amino acid. You can see also, for example, if you look at methionine, same sort of thing. Yeah, it's a methyl, so it's a neutral amino acid. You contrast that with, say, arginine, and here on the alpha carbon we have this large group, and you can see that it's decorated with a lot of nitrogen. These nitrogens, of course, are beautiful Lewis bases or Lewis donors. So, of course, yeah, this is a basic amino acid. Same thing with histidine. You can see, for example, histidine has on its R group this pyrrole nitrogen, and which is quite a nice donor. And so again, it's basic. If you look at aspartic acid, look, of course, acid, you can see here's our amino acid, here's the alpha carbon, and flanking the alpha carbon or attached to the alpha carbon, of course, that R group, and you can see that R group contains a carboxylic acid. So the species itself is an acidic amino acid. You can see exactly what's going on here. For example, we got proteins built up of different amino acids. You can see we can get to that's a primary structure. Here we got the ribbon system, so it's beta sheets. Of course, it's a secondary structures, and of course you can see we got tertiary structures and quaternary structures as far as these proteins are concerned. And we just covered this. You can see again where aspartic acid, yeah, has a R group which has a carboxylate. Here histidine has the R group that has, yeah, a basic nitrogen. So it's basic. Apart from proline, all other amino acids are primary amino acids. So you see proline is secondary because it's got two R groups attached to the nitrogen. Yeah. You can see the zwitterine nature because under metabolic conditions, this neutral form does not exist. In fact, the proton transfer realizes the zwitterion, which is the neutral form that exists. You can see here the ammonia species exists, and the carboxylate species is the one that exists. So in total, it's neutral. This zwitterionic species is in equilibria with the basic species and the acidic species. On the low pH conditions, you can see that protonation of the carboxylate will occur, and also protonation of the amine will be preserved. So now you have an ammonium species and you have your carboxylic acid. On the basic conditions, i.e. low pH, then deprotonation of the ammonium species occurs to give you the amine, and deprotonation of the acid to give you the carboxylate. Yeah? Occurs. So we can ask a question like this. 7.3, of course, is metabolic pH. Yeah? Most popular metabolic pH. And so you can see that would have a zwitterion. I mean, this is the form that would exist in acidic, yes? That's on the low pH. Yeah, this form does not exist because that's a neutral form, which we know it exists, the acid exists as a zwitterion. And here you can see, this is a really weird one. I don't think this is possible either because you got two basic ends and then acidic. That's not very good. And this one you can see is, of course, looks quite basic. If we titrate our acid typical titration of our acid, yeah, with some hydroxide, for example, so as you can see this increased basicity, yeah, we get to an isoelectric point. The isoelectric point is the zwitterionic form. You can see that above the pKa of the acid group, then the basic system would, yeah, be realized. And you can see below the pKa of the amino group, then of course the acidic species will dominate. So we come to a question like this, and it's very easy to calculate the isoelectric point, in this case arginine, because all you got to do is to realize that this R group is basic in nature. Yeah, so the whole species is basic. So as an approximation, I can ignore the pKa of the acidic group, and all I do is add these two guys together, yeah, and divide it by 2. So we average the two groups that are significant, yeah, and the significant groups are of course the two basic units. You divide that by 2, and of course you add them and divide it by 2, and that should give you 10.76. You can see here, if we look at the table, you can see that all of these guys, all the way down to cysteine, all of these guys are neutral amino acids. You can see that there is no pKa associated with them. pKa3 associated with them, i.e. that's the pK of the side chains. So all you got to do to calculate the isoelectric point is just add the pKa of the acid group and the pKa of the ammonium group, divided by 2. And here you get 5.98 for leucine. If you look at glutamic acid has a side chain which is acidic. Why? Because the pKa of that side chain is less than 7. So what we should do, therefore, is ignore the basic pKa, because the acidic groups are the significant groups. So you add those two together, yeah, and divide it by 2, and you should get 3.22. Try this with arginine. Exactly. You will ignore the acidic portion because that's, yeah, not relevant to us. And then you add the two base species together and divide them by 2, and that gives you 10.76. So synthesis, the only synthesis we're asking you to realize right now, or to remember, are these 3. You'll be familiar with these 2. Just a slight derivation here, and then this one will be fairly new, but something that I think you'll have a grasp of. You can see we can generate this halogenated alpha acid or alpha halogenated acid by the Helmholtz-Zielinski reaction. If you remember rightly, we have our acid, you treat it with phosphorus tribromide in the presence of bromine, and of course the bromination takes place. Now we can have the bimolecular attack of the ammonium. So use the large excess of ammonium, it's okay. Yeah, I have the bimolecular attack of the ammonium, and that will give us our amine. Remember, yeah? Alright, so that's the salt as your byproduct. That's your amino acid. You can see, for example, if we're going to make valine, yeah, you have this acid with the isopropyl, yeah, brominated, and then, yeah, substitute the amine, and there you have valine. In the case of the malonic ester, you should remind yourself of this synthesis, because if I decorate this, so I basify, followed by alkylation, or treating with the alkyl halide, I will get the alkylated form of my it's not working for me today. Get the alkylated form of my malonic ester. So if we do this real quickly, you can then saponificate and then heat. Try to come up with a product, will you? You should realize that the product is, of course, the acid. Well, we can use this species here that is decorated with an amide, and we do the same thing, because remember you have a proton right here which you can deprotonate. So you deprotonate that and form your enolate, and then the species that is realized So this is the alkylation. You can see that on saponification, or I shouldn't say saponification, on hydrolysis, because hydrolysis, of course, will be, well, hydrolysis of these groups, the esters, will realize the acids, but hydrolysis of this amide would realize the elimination of an acid plus the production of some sort of amine. This is what occurs. So on heating this product, then of course you can see the decarboxylation taking place to give you, yes, your amino acid. Let's have a look at exactly what this is. So deprotonation, attack, and then of course here's the derived species, which then is hydrolyzed followed by heating. Remember that this, yeah, is a beta ester. So on saponification followed by heating, we have decarboxylation. This is just Strecker synthesis, and all it is really, you got the ammonium chloride, which is a source of ammonia, will give you, yeah, some type of imine which then gets attacked by the cyano group to give you the alpha amino nitrile. Remember that we can hydrolyze this acid, this nitrile group using acids, and that realizes your amino acid. You got to start with an aldehyde. The mechanism looks like this. So you can see the ammonium forms the imine, which then gets activated and then of course gets attacked by the nitrile. Herein, once you get the amino nitrile, then you can hydrolyze to give you your amino acid. With peptides, there's not a lot we need to learn about peptides for this semester. All we got to do is realize that the peptides are of course polymers or small polymers of amino acids. So you can have like dipeptides, tripeptides, etc. The peptides are joined by amide bonds. So the combination of two or more amino acids, yeah, via an amine and an acid group gives you, yeah, an amide bond. So in a tripeptide, you would have two amide bonds. You can see in a dipeptide, you only have one amide bond. It is standard that you have the acid group on the right and the amine group on the left. We say this is the C terminus. The C terminus. And this one is here at this end, we call it the N terminus. That's definitely terminus. So N and C. You can see N terminus, C terminus. So for example, in alanine combining with cysteine, you can see immediately, yeah, the amine, yeah, will substitute the here, yeah, and so you end up with the amide. The amide, the bond, this amide system, amidic bond, yeah, of course is called the peptide bond. And herein, you can see that we have alanine being the N terminus and cysteine being the C terminus. So it's alacis. The reverse could happen as well, where you see the cysteine, yeah, the cysteine, yeah, is literally at the N, and the alanine is on the C. I think that's it, right? Yeah, alanine, cysteine, cysteine, alanine. Exactly. Totally different combination total different properties. The structure, you can see that the amidic bond, got this resonance, of course, so there's a lot of C double bond in characteristics. So this whole system is planar. So all 6 atoms here are in the same plane. And so that's why when you look at amino acids and when they combine to form peptides, the planar nature realizes these peptides look a bit like ribbons. Another thing, another feature of this is that because of the electronics, or even steroids, they exist in an S-trans arrangement, and so we got that zigzaggy sort of feature. Okay. Something like this you could simply ask, says, which is not a tripeptide, and you should realize by now that the right hand side has got the C terminus, and this left hand side has got the N terminus, and you got 2 amidic bonds here, 2 amides here and here, so that's a tripeptide. I just push down here and you can see, for example, that we have a C terminus there, and if you look carefully at this lot, you have an N terminus over here, and you can see that we have one peptide here, the amide is here, and the amide is here, right? So that's definitely a tripeptide. You can see an N terminus over here, which I don't think it's a terminus actually. That's part of another amino acid. So because here's an alpha carbon, and so that's an R group. So it is, you'd have to have the C terminus here, right? So don't make that mistake. So you have a C terminus here, right? And you have an amidic system here, and an amidic system here. But I can't seem to find an N terminus. There's no amine group over this side, and so this is definitely not a tripeptide. This is definitely not a tripeptide. You can see, stuff like this cyclic peptide, bradykinin, and bradykinin, for example, this peptide, is very important for blood vessel and pain, and of course oxytocin and vasopressin. There's only one difference, or a couple of differences in their setup, and of course you can see there's a difference here and here. I think that's the end of that, and of course we'll look forward to the exams on Monday.